Okay, in the last lecture, we defined the variables that we could sort of see in circular motion, the kinematic variables that might help us describe circular motion, radius, circumference, period, frequency. We describe the velocity as in the forward direction, that the velocity changes as we go around the circle because the angle of the velocity vector changes, and velocity is something with both magnitude and angle. But the speed doesn't necessarily change. The speed, if it's uniform circular motion, we're talking about constant speed. So the reason why the velocity changes is simply because the angle changes, not because the speed changes. You could have both change, but we won't probably talk about that anytime soon. So this is where we left off last time, but I did forget to define one thing, which I should have defined, and that is what is the speed, right? In terms of the other variables, the speed, if we're going in uniform circular motion, so for UCM, for uniform circular motion, the speed is not changing. So we can just take the total distance over the total time, right? The speed, remember, is the magnitude of the instantaneous velocity. So the speed really would be the amount of distance, right? The arc length here, the arc length, which we could call ds, and the amount of time that it takes that arc length, which we could call dt. And so that would be the instantaneous speed, or the instantaneous velocity. We could take the magnitude of that in order to find the speed, ds dt. So it's that distance divided by the amount of distance that it takes to, the distance that it goes divided by the amount of time it takes to go that distance. So if we want to find the speed, an expression for speed other than ds dt, we can say for uniform circular motion, ds dt is just going to be the total. If we can take a little section and say for a little section ds, it takes a little time dt, we know that the whole circle, the arc length of the whole circle, is just 2 pi r, the circumference, and the amount of time it takes is t, the period. So the speed for uniform circular motion is 2 pi r over t. That is the speed at any instant. That's not average speed. That's the speed at any instant. It is also the average speed, but the average speed is equal to the speed if you're traveling at constant. Okay, I've got to be careful because we're not traveling at constant velocity. But in this case, we are able to make the argument from this infinitesimal, we can find the speed for one instant, and then we just add it up as we go around. Okay, so the speed is 2 pi r over t, or also since period is 1 over frequency, it's also 2 pi r times f. You can write it either way, or you can even see that that's the circumference, so it's the circumference over t, or the circumference times f, whatever you want. But that's the speed for that an object goes in uniform circular motion. But let's contrast that to what is the change in velocity for the object at any point. The change in velocity for the object, let me try again. What I really meant to start with is what is the average velocity for at any point. The average velocity at any point is the displacement, delta x over delta t. And this is two-dimensional motion. So, the displacement between any 2 points is, if v1 is where it starts and v2 is where it finishes, the displacement is actually that length. What is that called? It's called a chord. That chord length divided by delta t. That is not a useful quantity. Honestly, it's just not a useful quantity. It doesn't really tell us anything about the motion. But for a full revolution, for one full revolution, what is delta x over delta t? Well, last time we showed that delta x for one full revolution is 0. So the average velocity for one full revolution is 0, right? For one full revolution. So you've got to be careful, because at any point, it's got a velocity that points in the direction of motion. It's got a speed which is finite and doesn't change. But the average velocity in one full revolution is 0. Because, right, when you get back to where you started, you got the same velocity you had when you started. So your Wait, no, that's not y. I keep on saying that wrong. You got the same position as when you started. So for one full revolution, delta x equals 0, so the average velocity equals 0. But it's not 0 in general, right? I mean, for the average, the change in position, for example, we just showed it, right, is not 0 until you go all the way around a circle. Okay, anyway, let's move on from that. What about acceleration? Excuse me. Acceleration. Well, acceleration, remember, is defined as dv dt. And so then you might say, it's traveling constant velocity. There is a constant velocity. There is no acceleration. Well, first of all, no, it's not traveling constant velocity. The velocity changes because the position. I keep saying it wrong. Because the angle changes. It's traveling at constant speed, but not constant velocity. So the fact that the angle changes as it goes around the circle means that it is accelerating. And actually, when we get to the force chapter, it becomes very obvious because there is a force on this object, right? In order for the object to go in the circle, let's just say that this is a ball on a string. There's a string, right, which is pulling it towards the center of the circle. It's holding it in the circle. Let's even say this is a runner on a track, a runner going on a circular track. Well, why is the runner staying in a circle? Why, what is keeping them from going in a straight line? If you got rid of friction, what would happen to the runner? That runner would slide right off the track and go in a straight line. Right? It's friction that's holding the runner on the track. There's always a force keeping you in a circle. And so the fact that there's always a force, Newton's laws tell us there must be an acceleration. Of course, that's getting ahead of ourselves. That's the next chapter. But let's just look at this from the point of view of dv dt. If we understand this, we can quite easily see that at any instant there must be an acceleration. There must be an acceleration because that velocity vector changes. So, for example, let's just take in the picture that we have, right? This is position 1 and this is position 2, and let's just pretend those are relatively close together, right? They're close together, so we can talk about a dv dt, right? A small change in velocity over a small change in time. So at any instant, we can always talk about, right, v1 is in that direction and v2 is going to change slightly, right? It's going to be in a slightly different direction. At any instant, as each instant goes on, the velocity vector is going to change in direction. So this is just v1, this is v2. We want to find dv. dv is v2 minus v1. That is the definition of change in velocity. dv means change in velocity for a small change in time. We've got to make sure we understand that dv is like delta v. It's defined as delta v for a small change, right? So it's just for a small change. That's really all the little d means instead of delta, small change. Not an as small change, but a small change. You saw the difference there, right? As small, I look like I had a space in the wrong place. A small change. Okay, so dv is v2 minus v1. How do I do v2 minus v1? Let me go to the next page. I have v1, and just an instant later, so it's just a small change, I've got v2. But I want to know what is dv. dv is v2 minus v1. So I've got to rewrite them. V2, I'm going to try to draw a good picture here. Let me rewrite V2. This is V2. Let's pretend it is. I didn't draw that terribly parallel. Minus V1. So V1's got to turn around. V1 is now, this is minus V1. And so dV points from the tail of the first to the head of the second. So this is dV. So the vector dV, right, there is a vector dV. And acceleration is dV dt. Okay, so what this shows us is the direction of the acceleration. The direction of the acceleration is not in the direction of the velocity, never was. Even in two-dimensional motion, it was often not in the direction of velocity. But notice what the direction of the acceleration is if I look at V2 and V1 on this picture here, that the direction of V2 minus V1 points this way. Points this way. v2 minus v1 points that way. And if I draw this really carefully to scale, what you'll find is that points towards the center of the circle. dv dt, the acceleration, points towards the center of the circle. We just do a careful drawing of v1, v2, and do a scale drawing, and you can see that dv points towards the center of the circle. So the acceleration points towards the center of the circle, which makes perfect sense. Because think about the ball on the string. What was holding it in the circle? The string was exerting a force right towards the center of the circle. And Newton's second law tells us the forces and the accelerations are proportional. So the acceleration must point towards the center. That's next chapter, though. You don't know Newton's second law yet. Okay, so the acceleration points towards the center of the circle. So that's one interesting thing, is that for an object moving in a circle, there is an acceleration towards the center of the circle. So I'm not sure if I was just recording when I said that, so I'm going to say it again. For an object moving in circular motion, there is an acceleration pointing towards the center of the circle. Actually, for an object moving in uniform circular motion, there is an acceleration pointing towards the center of the circle. If it is not uniform circular motion, this is important for later, not for right now, but it is important for later. If it's not uniform circular motion, it means it is also changing velocity. So that means that there is still an acceleration towards the center of the circle because it's moving in circular motion, but there is also a component of acceleration tangential to the circle if it's not uniform. Okay, I just wrote down what I said there. But what's important here is the picture. That was just meant to indicate it's going around the circle like that. Is the picture here is that the velocity is always tangential and the acceleration for uniform circular motion is always center seeking. It's always towards the center. It's called the center seeking, right? The acceleration. And center seeking, which is therefore is called centripetal. Center seeking or centripetal means center seeking. Centripetal. So this is the centripetal acceleration. A sub centripetal. But that's a lot of words to write, a lot of letters to write, so we just call it A sub c. We know that A sub c is the center seeking acceleration, is the circular motion acceleration, or just A sub circular. But it's really it's the acceleration in the circular motion. Okay, centripetal means center seeking, A sub c. So let's go ahead and derive what is A sub c, an expression for A sub c. Well, let me go back and remind you that V for uniform circular motion, this is UCM, uniform circular motion. V is 2 pi r over period. V is 2 pi r over period. Now, we're going to use a mathematical argument here. It is a completely valid argument, but it's a mathematical argument. You've got to pay a little bit of attention to understand. If this is my radius vector, right? My radius vector, think about what happens as my object goes around the circle. My radius vector traces out a circle, right? The tip of my radius vector traces out a circle, which has a arc length of 2 pi r, and it takes a certain amount of time t to go around that circle. And so we can find that the speed is 2 pi r over t. Not velocity, but speed is 2 pi r over t. So now think about the velocity vector. The velocity vector looks like that, and like that, and like that, and like that, as we go around the circle. And think about, what does the velocity vector do? The velocity vector, right? Let's put all those velocity vectors so that they're tail to tail, right? What does the velocity vector do? The velocity vector does the exact same thing that the radius vector does. It traces out a circle. The velocity vector traces out a circle in a time t. So that means we can actually make the argument by that, by that argument, we can show that the acceleration must be 2 pi v over t. If velocity is 2 pi r over t, and the radius vector, because the radius vector traces out a full circle of circumference 2 pi r, then the velocity vector must also, the velocity vector does also trace out a circle with circumference 2 pi v, and the acceleration since it's defined in terms of velocity in the exact same way that velocity is defined in terms of distance, the acceleration must be 2 pi v over t. But since v, so this is the centripetal acceleration, a sub c. Since v is 2 pi r over t, so therefore we can make a substitution and say that this is 2 pi times 2 pi. Hold on a second. What I was about to write is correct, but it's not useful. Whoopsies. I'm going to make a substitution for t, right? So from the first one, we can say, okay, therefore t is equal to 2 pi r over v. And so we can plug that in here and say that centripetal acceleration is 2 pi v over t, which is 2 pi r over v. The 2 pi's cancel, and the v's go v squared over r. So therefore, the centripetal acceleration is v squared over r. That is the acceleration of an object moving at constant speed. Or it's actually the acceleration of an object at any instant moving at speed v. So it doesn't actually have to be moving at constant v. It's the acceleration at any instant of an object moving in a circle at speed v. So we've now really defined all the kinematic variables for uniform circular motion, which is different than two-dimensional motion, projectile motion, right? It's different kind of motion. One other thing is we actually have a direction for the acceleration, so we can write this as inward, right? And what is inward? Well, inward changes, right? Inward can be the x direction, it can be the y direction, but if I were to put the circle on a graph and say, what is the inward direction? Well, when the object's on the right, the inward direction is to the left. When the object's on the top, the inward direction is down. Right? So the inward direction changes as we go around the circle. So the acceleration actually changes as we go around the circle, right? But the magnitude of the acceleration is constant, but the direction changes. It's inward. It's not x or y. It's actually the opposite of radial. I guess that's another way to put it. The radial direction, remember the radius points outwards, so it's the negative of the radial direction. This is actually a mathematical notation. This isn't my own. Minus of the radial direction. The radial direction, we already showed that a radius vector, going back to my circle up here, right? A radius vector points from the center outwards, and the acceleration points inwards. So it's the opposite of the radial direction, the opposite of the r hat direction.